right, so now we're going to look at some properties of the probability generating functions. We've already seen that a binomial expansion or a binomial distribution could be expressed with the probability generating function this way. I would do the same sort of idea for a geometric distribution, and I'll leave that to you to prove these two. Unfortunately, these are not in your formula booklet, so if you had a problem involving a Poisson, which is another discrete distribution, or a geometric, I would use the formula booklet to just find those probabilities and then use our idea of the probability generating function of being probability t to the x value. In the end, they'll simplify to this, but I don't think it's worth memorizing these. It is interesting to note these properties though. So even though I said t is a dummy variable, we do have some interesting things when we plug in values for t. So let me add a page here. So again, we saw that our generating function is sum for all our x values, the probability that x equals x, t to the x. So this becomes probability that x is 0 times t to the 0, probability that x is 1 times t to the 1, for as many x's as I have. So let's think first of g of 0. Well, g of 0, I'm going to replace all my t's with 0. That's going to leave me just with the probability that x is 0, because this will have already gone away, because I know that t to the 0 is 1. Now let's look at g of 1. Well, g of 1 is probability of x plus probability of x equals 1, because that's going to be 1, probability that x equals 2 times 1, etc. Well, that's all my probabilities summed together, so that's going to be 1. Let's look at the first derivative. First, we can look at it at t. So that's going to go away. And then I'll have, this is going to be probability of x, that x equals 1, plus 2 times the probability that x equals 2 times t, 3 x equals 2 t squared, that's t, sorry, 3, this would be t cubed, 3, that would be t squared. Squared, 1, 3, squared. I wrote the same thing twice. All right, now I see why I'm confused. All right. Well, notice that if I do the first derivative at 1, I'm going to have probability that x equals 1. I could think of that as 1 times probability that x equals 1, plus 2 times the probability that x equals 2, plus 3, probability that x equals 3. Well, notice that that becomes the sum over the x values of x times the probability x equals x. Well, I know that as my expected value. If I think about my second derivative, well, that's going to go away. Here I'm going to have 2 times the probability that x equals 2 plus 6 times, and actually it's probably better if I keep this as 3 times 2. Over here this would have been 1 times 2. That one is x equals 2. This is, that was my mistake there. All right, so my next one is going to be 4 times 3 times the probability that x equals 4. I'm missing a t. This one is going to have a t. This one would have t squared, etc. But now if I plug in 1, then I'm going to have, I can shrink it down similarly, but this time I can write it as x times x minus 1. If I go the other way, probability that x equals x. And this is the same as the expected value of x times x minus 1. Well, if I expand that, that's e to the x squared minus e to the x. And I know this because of my original expected value calculations with linear functions. So that means if I'm thinking about my variance, well, I know that variance of x is e of x squared minus e of x quantity squared. Well, that's the same as e of x squared minus e of x plus e of x. So I'm looking at this thinking, how can I make that happen here? Well, this is like adding 0. I'm going to subtract e of x quantity squared. This is my second derivative of my generating function evaluated at 1 plus first derivative of the generating function evaluated at 1 minus first derivative at 1 quantity squared. So if we come back to this chart, that's where these values came from. Again, not in your formula booklet, so in this case they are useful to memorize. And this is expanded out again, something similar to what I just showed you.